Sorry I can't be with you today. Today we're going to talk about 7.3a, similar cross sections. Be a little bit different color here, about blue. So we're going to split 7.3 into two sections. Today we're going to do similar cross sections. Tomorrow we're going to do volumes of revolution around an axis. So before we jump into our volumes of similar cross sections, let's take a look at some bell work here. This is the problem 3 from your sheet. It's a little bit confusing when you put things in terms of y, but the point of this is if you integrated this with respect to x, we talked about the stick yesterday, so for a while your top function is supposed to be y equals root x. For a while your top function is root x and your bottom function is 0, so you just be integrating root x. But then when you get to here, you would have to change your function. So you have to figure out what this intercept is. It's probably 2. And then you would have to integrate with the top function as root x, but the bottom function would be what? Y equals x minus 2. And this is fine to do. You just have to figure out what those limits are. It looks like 0 to 2, and then 2 to, let's see, that would intersect at, I think, 4. Yes, with a question mark. Let's see, x minus 2 equals root x. You could square both sides, figure that out. Looks like it's going to end up at 4. Yep. So 4 of top function is root x minus the function x minus 2. But this is kind of a pain because you have 2 steps you have to put it in, and you would have to break it up there, find this intersection point, all this mess. Instead of doing that, what you can do, and that's perfectly fine way to do it if you want to. Sometimes they give you functions that are harder to change. But if we use a stick that is horizontal instead, look at this. The entire time, if you do right minus left, so remember we talked about this, if you integrate dy, you have to do right minus left. So I could integrate from y equals 0, so this is y equals 0, up to y equals, I think it would once again be 2. Let's see here. 2 plus 2 is 4. 2 squared is 4. Yep. So from 0 to 2, right minus left. So it'd be y plus 2 minus y squared dy. And let's see if we get, see what we get here. So integral 0 to 2, negative y squared plus y plus 2 dy. Antiderivative, negative y cubed over 3 plus y squared over 2 plus 2y, evaluated from 0 to 2. 2 gives us negative 8 thirds plus 4 halves plus 4. So that's negative 8 thirds plus 2 plus 4. You could leave it any one of these spots, but let's see if we can make it happy. 4 and 2 are 6. 6 is 18 thirds. So it'd be 18 minus 8 over 3, which is 10 thirds. So just kind of a cool alternative way to solve these problems if you can use a stick that will always have the same right and left as opposed to having to change top and bottom by doing x's. Definitely an advantage. And the hint here they give you is they give you everything in terms of y. So a typical AP problem that you might have for area like this is they might tell you, like, you have the function y equals x squared. So you have a parabola. They might cut it off at y equals 4. And they might say there's some line, y equals k, that divides the area of the top and the area of the bottom into equal sections. So they want some k value here so that the area above and below is the same. So area above k and below k are equal. And they might say, what's k? So find k. Well, for this problem, if you integrate dx, I'll change my color here so we can show this. If you integrate dx, it's going to be top function of 4 for a while, bottom function of x squared. Then it's going to change to just top function 4, bottom function k for a while. Then it's going to change back right here. So you have to do 3 separate regions to do that. That is a pain and a half. Instead of doing that, what I want to do, just got rid of my function, I'll put it back in. What I want to do is I'm going to use y instead. There we go. Okay, so try to make those two areas equal. So if I integrate dy, my bottom integral will be from 0 to k, and that would have to be equal to the integral from k to 4. Now we just have to figure out what our bounds are. Well, if we solve this for y, we have x is equal to the plus or minus the square root of y. So the right side would be the positive, the left side would be the negative. So we do right minus left, so it would be root y minus negative root y dy. And same thing on the top. Right function minus left function is still the same. So it's just root y minus negative root y dy. So we have is integral 0 to k, 2 root y dy is equal to integral from k to 4 of 2 root y dy. So we pull those 2's out, they actually cancel, because we can divide both sides by 2, they go away. Antiderivative of root y, that's y to the 1/2, would be y to the 3/2 times 2/3. Evaluated from 0 to k has got to be equal to, same thing, 2/3 y to the 3/2, evaluated from k to 4. So thankfully when we plug in 0 here, it's 0. So what we have for our equation is k 2/3 k to the 3/2 is equal to 2/3, so 4 to the 3/2, square root of 4 is 2, cubed is 8, so I'd have 2/3 times 8 minus 2/3 times k to the 3/2. 2/3 we can divide out everybody. So if I add k to the 3/2 to both sides, I have 2k to the 3/2 is equal to 8. Divide by 2, that's 3/2, sorry. Divide by 2, we have k to the 3/2 equals 4. Take both sides to the 2/3. K is 4 to the 2/3. That's not a great number. A cube root of 4, I don't know what that is, so I just leave it like that. Or the cube root of 16, I guess you could also do, because 4 squared is 16. So kind of cool that we can find that value that actually splits the area exactly in half. Really typical AP question. They'll say, what's the line that splits this area in half? And this problem, way easier to use y's than x's. Kind of cool. Okay, so we're going to intro into this idea of a volume in terms of cross-sections by talking about the volume of a cylinder first. So let's say we have a cylinder, and usually I think people think of cylinders like this. And let's say the radius is 5, and the height is 7. We want to find the volume of the cylinder. Well, volume of the cylinder is the area of the base, pi r squared, times the height, which is 7. Makes sense to me, because it's almost like you have 7 cylinders here. 1, 2, 3, I'm not going to fit 7. 4, 1, 2, 3, 4, 5, 6, we need one more on the bottom. So it's almost like you have 7 of these discs, and each one of them has like an area or a volume of pi r squared, which in this case would be, that should be pi r squared h. So this would be pi times 25, pi r squared, times 7, which is 175 pi. Now there's a different way to do this problem, and it kind of is gotten at by thinking about separating these into disks. If we put this on an axis instead, so this would be x is 7, and our radius is still 5, so this I guess would be 5 and negative 5. And if we think about taking like a cross section here, so if you sliced this with a plane, that would give us a cross section here that's a circle. And I think you agree with me that no matter where we put this plane, from 0 to 7, every one of them would have the same cross section. It would have a radius of 5. So the area of that cross section that has radius 5 would be pi r squared, which is pi times 25. And how many of those circles do we have? If you think about sliding this plane left and right, how many circles of those happen? Well, there's an infinite number of them. Adding up an infinite number of things sounds like an integral. We're adding up from 0 to 7, the same thing over and over again, 25 pi. And this would be dx, because we're moving that plane along the x-axis. So we could pull the 25 pi out. The antiderivative here is 25 pi x. 25, oh my gosh. 25 pi x, evaluated from 0 to 7. 7 plugs in, 25 pi times 7, which is 175 pi. The 0 will just give us 0. So just kind of a cool way to see that we can use integration to do this. The general formula that we're using there, yeah, we'll put it in here, is the integral from a to b of the area in terms of x dx. Now in this case, it didn't matter what my x value was. Every single x value gave me an area of 25 pi, or 25 pi. What we're going to get to today are some where the area actually changes depending on the x value. And it still works the same way. You just integrate the area in terms of x from a to b, whatever those values are. But just kind of a simple introduction to see that we can use these cross sections. We call this the representative cross section. Cross section. And then we just integrate it on the terms that we want. So you can actually create some pretty cool volumes with this. This guy looks like it has a base of a circle. And then at each width of the circle is the base of an equilateral triangle, it looks like. So in the middle, we have the biggest triangle. And then on each edge, we actually go all the way down to a triangle of size 0. And it creates this kind of curving point at the top that would be also semicircular. Here we have some different options for cross sections. Looks like this are squares that are popping out. The base is the length or the height of the function. These look like semicircles. These look like right triangles. And these guys look like rectangles that probably have a height that's half of the length or something like that. So different cross sections that you use create these really unique volumes. And tomorrow in class, I'll see if I can get some from, I believe Mr. McManus and Mr. Schofield actually have some of these in their rooms. But what we're using here is we're using a function down in the xy plane, and then these guys are actually popping out of the graph. They're popping out of the graph to create these different cool volumes. And that formula, again, we just integrate from a to b, the area in terms of x dx. So you can see here the area of every one of those cross sections is going to be different. It's getting bigger as the function gets taller. Each one of these gets bigger as the function gets taller. So as x changes, as x goes along its little axis here, each one of those areas will be a little bit different. We have to add them all together to find the volume of that object overall. So let's try a problem. Oh, sorry. First I have this, it's kind of a cool animation. So they have a quarter circle here, and they're doing this idea of using the base as a square. And it's going to end up creating a real nice visual of what this would actually look like, this volume. So let's kind of like let it go and see what it ends up looking like. Notice the squares get bigger as you go because that semicircle gets taller as you go to the left. And to add all of those up together to get an area, you would have to use an integral. Kind of cool. All right. So here's our first example. Base of a solid is the circle centered at the origin with radius 3. Let's graph that. So 3, negative 3, 3, and negative 3. So this is the base of the solid. The solid has semicircular cross sections with diameters that lie in the xy plane perpendicular to the x-axis. So what that means is if we think about the stick, perpendicular to the x-axis, right? So the stick here, these are all going to be diameters of circles that are popping out of the screen towards you. So the way you usually see this done is you lay down the circle. So we're going to kind of try to graph in 3D here. So our circle looks something like this. And what happens is each value perpendicular to the x-axis is going to be the diameter of a semicircle. So our tallest semicircle is going to be in the middle here. And each one of these is going to have a semicircle. So can you think about what that shape is actually going to look like? It's really hard to draw. But if the biggest semicircle is in the middle, and at the edge, if it goes all the way down to 0 where there's nothing, it's going to end up looking like half of a sphere. It's going to be half of a sphere, or a hemisphere. is a hemisphere with a radius of 3. Now we're going to use calculus to be able to actually figure this out. At each x value here, the diameter is going to be different. It's going to be according to the function of the circle. But the volume of a sphere is 4/3 pi r cubed. And if we plug in our values here, so the hemisphere is going to be only half of that. But that would be 4/3 pi times our radius is 3, so it'd be 3 cubed. That's 27. Divided by 3 is 9 times 4 is 36 pi. So when we do this with calculus, we should get 18 pi, because it's a hemisphere. It's only the top half of the sphere. Let's see what happens. So each one of these semicircles has a diameter that is the distance between the top and bottom of this circle. Well, a circle with radius 3, the top half of this semicircle equation, good thing to know, square root of 9 minus x squared. The bottom is going to be negative square root of 9 minus x squared. So the radius of each one of these semicircles that's popping out of the screen will be the distance from the x-axis to the top of the circle, which is the square root of 9 minus x squared. 9 minus x squared. So the area of this, I call it a of x, and I'm going to encourage you guys to do this every time. Draw one of the representative cross sections. So if we think about this, again, I'm just going to draw one of them. So like this guy right here. This would be like x is negative 2. So when x is negative 2, the radius of that semicircle is going to be 9 minus 4 square root, so square root of 5. And then we can find the area of this guy by plugging that into the area formula for a circle. So it's going to be pi times radius squared, which is pi times 9 minus x squared. So any value x, I think I've got another screen for this. So any value x, right, from negative 3 to 3, will give a semicircle that has that exact area. Okay? I should do 1/2, sorry, because it's only a half circle. So this is going to be the area of any value x from negative 3 to positive 3. So if I want to find the total volume, I just integrate. So we're going to integrate from negative 3 to 3. Each one of those x values has a semicircle, and the area we just found is 1/2 pi times 9 minus x squared dx. So that's our integral of the area of a single cross section. Because you know that radius was square root of 9 minus x squared. And now we just do the antiderivative. So pull out the 1/2 pi. Negative 3 to 3, 9 minus x squared dx. So it's 1/2 pi, 9x minus x cubed over 3, negative 3 to 3. That's 1/2 pi. 9 times 3 is 27. Minus 27 thirds is 9. And then minus negative 3 times 9 is a negative 27. And then negative 3 cubed over 3 is negative 27 over 3, which is negative 9, so we do plus 9. All in brackets. So that's 1/2 pi times 27 minus 9 is 18. Minus negative 27 plus 9. So negative 27 plus 9 is negative 18, so that's plus 18 again. So that's half 36 pi, which is 18 pi. And I believe it's exactly what we're going for. So we did it using geometry, just using the formula, and now we show that the calculus works out again. So wrapping your mind around this the first time is kind of tricky, because this idea that they're popping out of the board, right? So this is like coming out at you, and each x has a different cross section. But all the cross sections have a radius according to this function, because the stick is going to be, in this case, your diameter, and half of that, which is just center to top, will be your radius. All right, let's try a different one. Sorry, first, before we do that, the author of your textbook, I believe it's Finney that has this house. He actually built a house that is based on similar cross sections. So if you notice, the window line here is the same as the window line up here, same as whatever this wood stuff is up here. if you wanted to find the volume of this house, every layer would have a similar cross section. Kind of cool, very nerdy. The inside of that house is really cool as well. If you Google integral house, you'll be able to see some really cool stuff. All right, here's another one. So this time we're using the function x squared, and we stop it at x equals 4. And what we're going to have is the cross sections perpendicular to the x-axis. They're equilateral triangles. That means they have the same side. Okay? And they get bigger, obviously, as we go to the right, because the base will get bigger and bigger and bigger. So then each side gets bigger and they get taller and taller. So it's going to create this kind of parabolic, growing triangular shape. So let's see what we can do. So if I lay this down, here's our x squared. Here's 4. And each one of those is going to be an equilateral triangle. So as x increases, the base of the triangle is going to be x squared. So let's think about how we find the area of an equilateral triangle. Kind of a tricky thing. So if we have, let's say the bottom length is x, and then that would mean, if we draw on our triangle here, this guy would be x over 2. This is 60 degrees, and this is x right here. So if you think about it, sine of 60, what do you sine? Yeah, it's fine. So sine of 60 degrees, if we don't know h here, would be opposite of hypotenuse, h over x. So h is actually x times sine of 60. Sine of 60 is root 3 over 2, so this is root 3 over 2x. So in this case, draw a representative cross section. The base is going to have a length that is equal to the height of our function. Well, that's x squared. So we have x squared down here, and then our height is going to be root 3 over 2x squared. Area of a triangle is base times height, 1/2 base times height, excuse me. So we have 1/2 x squared times our height, which is root 3 over 2x squared. So overall, that is root 3 over 4x to the 4th. So this is the area of one of those triangles for any x value that you choose. We have to add them all up from 0 to 4. So we're going to get from 0 to 4, root 3 over 4 I'll pull out, x to the 4th dx. So it's root 3 over 4, x to the 5th over 5, 0 to 4. 4 to the 5th power, goodness. Big number, but check it out. It's going to cancel out with that 4 right there. So it's actually going to end up only being 4 to the 4th power. So root 3 over 4 times 4 to the 5th over 5. The 0 will just cancel out. I'm going to change this to a 4. Cancel it with that 4 right there. So 4 cubed is 64 times 4 again, I think, is 256. So we have 256 root 3 over 5. Whew. I believe it. Good problem. All right. Similar problem, just a little bit different. Same function, y equals x squared. What I'm going to do now is the cross sections are perpendicular to the x-axis, but they're circles with a diameter in the plane. So this is actually half of the volume, the picture that's drawn here. What I wanted to do is show you that they can also go below. So we have x squared here. So what's happening is if this is the diameter of the circle, it's going to go below and above. Okay, so we have kind of this expanding idea. And each one of those representative cross sections will be a circle. So let's draw that out. Here's our representative cross section. And the diameter is going to be our x squared. And so that means that the radius is x squared over 2. So the area of this guy would be pi times r squared. That's x squared over 2 squared. So overall, pi times x to the 4th over 4. And that's going to be true for every value between 0 and 4. So this would be my diameter. Circle comes out, drips down as well. All the way up to 4, we'll have our biggest circle coming out of the screen and also going into the screen. We have to integrate that from 0 to 4. So our a of x equation, I'll pull out a pi over 4, x to the 4th dx. So that's going to be pi over 4, x to the 5th over 5 dx. We've had this before. Plug in 4. One of these goes away. So it looks like 256 pi over 5. It's actually comparable in size to the last one. We had 256 root 3 over 5. This time we have 256 pi over 5. Pretty cool. So if you ask for units here, it'd be like units cubed, because it's a volume. All right. Here we go. Another problem. This one's got a little bit different spin. So we've got x squared minus 1. That looks like this. And we got 1 minus x squared, which looks like this. So we have squares that are perpendicular to the x-axis with one base in the xy plane. So square, something like this. Okay, so these squares are popping out of the screen. If we were to lay it down, have parabola like that, parabola like that. There's our square. So what's the length of the base of that square? Well, it's just the difference of the functions, right? So if we draw a representative cross-section, base of the square is going to be, looks like g of x minus f of x to keep it positive. G of x minus f of x is 1 minus x squared minus parentheses x squared minus 1. That'll add the 1 and subtract the x squared. So it looks like we'll have 2 minus 2x squared. Now we have to figure out where we integrate it from. We're going to integrate it from the intersection points. Looks like they both intersect at 1. If we plug in 1 here, we get 0. 1 here, we get 0. Yep. So we're going to integrate from negative 1 to 1. 2 minus 2x squared dx. Pull a 2 out of there. So it'll be 2 times x minus x cubed over 3. Negative 1 to 1. To plug in the 1, we have 2 times 1 minus a third minus negative 1 plus a third. You'd stop there, but let's see here. So 1 plus 1 is 2 minus 2 thirds. We got 2 times 2 minus 2 thirds. It's 4 minus 4 thirds, which is 12 minus 4 is 8 thirds. Cool. So you can see the math isn't really that hard once you can figure out exactly how you're going to find the volume. We just integrate between the intersection points. Base is a square, so the base is the distance between the top and bottom functions, and then we square it. Oh, I messed up. Did you guys see what I did? This is the length of the bottom, but if I want the area of this square, what should I have done with this? Should have taken that value and squared it. Oh, Fransky. That's a bummer. Well, let's go back and do it. Why not? You can skip this part if you want to, but I'm going to go back and redo this integral here. So the area is going to have this squared. So if we multiply that out, integral negative 1 to 1, 4 minus 2 times the first times the second, which will be 8x squared, and then plus 4x to the 4th dx. So that'd be 4x minus, let's see here, 8 thirds x cubed plus 4 fifths x to the 5th. Evaluated from negative 1 to 1. So we got 4 minus 8/3 plus 4/5 minus -4 plus 8/3 minus 4/5. I'm going to leave it there this time. You can do the algebra if you want to, but I just forgot to square it because that's going to be the actual a of x. It would be the base squared. So it would be g minus f squared. Cool. Sorry about that little mishap with the square. All right, so these are going to be some useful area formulas for you. This is one we actually derived in the triangle problem we did, but if s is the side length, well, I got it right here, then you can do √3/4 s squared for the area of an equilateral triangle. If you have the side length of a square, obviously the area is s squared. If you have the diagonal of a square, this is important for one of your problems, you can get the area with a little shortcut, 1/2 d squared. And then if you have a right triangle that has the same length on both sides, so it's an isosceles right triangle, 1/2 base times height, which would be 1/2 x squared, s squared, or you can do the 1/4 d squared using the diagonal as well. So your homework tonight, only 6 problems. They are tough. Make sure you try them. Try, try, try. Look at the solutions manual if you have to, but keep going at it until you get the right answer, because it's very satisfying when you do, and it's really, really good practice. So that's all I've got for you. I love you guys. That's why I'm here. Have a great day, and I will see you tomorrow. Love you guys. Bye.